projects underway.
Oh, shit. You win.
Good morning, good morning, good morning.
Morning.
Good morning.
Time for roll call. Time for roll call. Listen for your name. Let's start with group number 1. Group number 1.
I'm here, Professor. Maribel Rosas from Group 1.
Huh?
Maribel from Group 1.
Yeah, I'm going to do group 1 now. Okay, how about Schutz? Are you here?
Who?
Dennis Schutz?
I'm here.
All right, good for you. Welcome, welcome, welcome. Fernandez? Jasmine?
I'm here.
All right, good for you. Welcome. Maria Lopez?
I'm here.
Good for you. All right. Maribel Rosas?
I'm here.
Good for you. Carter?
I'm here.
All right. Good for you, Carter. Welcome. Raleigh?
I'm here.
All right. Eden?
Here.
Very good. Out of group 1 are present. Good for you, group 1. Let's move on to group 2. Masha? Chanel, Masha? Not here? Okay. Whitlock? Whitlock was not here yesterday, they're not here again today. All right. Christina?
Professor, I'm here.
Who?
Christina Constable.
Christina Constable, all right. Welcome.
Thank you.
All right.
Hello. Hello, Professor.
All right. Who's talking?
Chanel Marshall.
Chanel Masha, welcome.
Thank you.
All right. Jasmine Zacharias?
Here.
Very good. Welcome, welcome. Stevens? Tenora Stevens? Not here yesterday, not here today. Okay. Janelle Green? Janelle Green. Group 2. Not here. Pete? Demisha?
I'm here, Professor. Did you say Tamisha Pete?
Yeah.
Okay, I'm here.
Welcome, welcome.
First patient before.
Okay, now move on to group 3. Tiffany?
Here.
What's your last name, Tiffany?
Carskio.
All right, welcome home.
Thank you.
All right, Elizabeth.
Here, Professor.
Elizabeth, what's your last name?
Otignano.
Oh, good for you. Welcome home.
Thank you.
All right. And Angel?
Christy Gutierrez Angel.
Yeah, how about that? Welcome home.
Thank you.
How about Jason?
I'm here, Professor.
What's the last name?
Calderon.
All right, welcome home.
Thank you.
All right, Dorothy,
I'm here.
last name?
Lautoa.
Atoa, welcome home.
Thank you.
Ariel? Anna?
I'm here.
All right, Anna, welcome home. All right. Mercury? Edwards? Mercury Edwards?
I'm here.
All right. So that's moving on to group number 4. Cynthia Chavez,
I'm here, Professor.
good for you. Welcome.
Thank you.
Shante Brewer was not here yesterday, not here today. Okay. Ashley?
Yes.
Okay. Ashley, what's your last name? Ashley, what's the last name?
Gutierrez.
All right. Welcome home. Robin,
I'm here, Professor.
what's the last name?
Ben Alonso.
All right. Welcome home. Okay. Stephanie?
Hi, Professor. I'm here.
Okay. What's the last name?
Mendes.
All right. Welcome
Thank you.
home. Estella,
I'm here, Professor.
last name?
Arroyo.
Welcome home.
Thank you.
Okay. Adrina?
Adriana Velasco, I'm here.
Yeah, welcome home.
Thank you.
Okay, group number 5.
What, Professor?
Hmm?
I'm so sorry. I am just barely getting in. You called for Janelle Green,
Janelle Green?
group 2.
Group 2, welcome home, Janelle.
Yes, thank you.
All right. 5.
Hello, Janelle.
Huh?
I said, hello, Janelle. It's Chanel.
Janelle?
Yeah, Janelle, I'm saying hi from Chanel.
Oh, how are you?
I'm doing well.
All right, good for you. Group 5. Thomas. Is Thomas here today? No? All right. Devin?
Hi, I'm here.
Devin, what's the last name?
Martinez.
All right, welcome home.
Thank you.
All right, Oscar. Oscar was here yesterday, then not here again. Okay.
Hi, Professor. I'm here.
Oscar, you were not here yesterday.
I was not.
You're absent, right?
Yeah.
All right, good. Okay. All right. And Dana? Diana?
I'm here.
What's the last name, Diana?
Brilliances.
All right. Welcome home.
Hi,
Alyssa.
Professor.
Alyssa?
Here.
Is that you, Alyssa?
Alyssa Gomez, yeah, I'm here.
All right. Welcome home. All right. Tello? Is Tello here?
Yeah, I'm here.
All right. What's your first name?
Christiana.
All right. Welcome home. All right. Nibla?
I'm here.
What's your first name?
Lolly.
All right. Welcome home. That's group 5. Now move on to group number 6. Nora?
I'm here.
Nora, what's your last name? Huh?
Thanks. HAMS.
All right. Welcome home.
Thank you.
India?
I'm here, Professor.
What's your last name?
Sanders.
And nice home, nice home, nice home. All right. Claudia,
I'm here.
last name.
Robesa.
All right. Welcome home.
Thank you.
Rebecca.
Here.
Rebecca, what's your last name? All right. Welcome home. Carmen,
I'm here.
what's your last name, Carmen?
Bias.
Yes, welcome home.
Thanks.
Okay. Pointer? Huta?
I'm
What-
here.
What's your first name?
Tiklali.
Declare. Welcome home. Group number 7. Courtney.
I'm here.
Courtney, what's your last name?
Jones.
John, welcome home.
Thank you.
Jose. Jose, group 7. Jose not here today, okay. Rosa. Rosa, not here today. Okay. Vencolo.
Yeah, I'm here.
What's your first name?
Ciara.
Tiara, welcome home.
Thank you.
Andrea,
I'm here.
what's your last name?
Bias.
Yes, welcome home.
Thank you.
Jennifer,
I'm here, Professor.
what's your last name?
Cervantes.
Cervantes, come on home, come on home.
Thank you.
All right. Group number 8. Marika,
Here.
last name?
Trasminia.
Yeah, welcome home. Shira. Shirel, not here today, okay. Haley,
I'm here.
what's your last name, Haley?
Herrera.
All right, welcome home. Annie,
I'm here, Professor.
what's your last name?
Ocampo.
Yes, welcome home.
Thank you.
Hernandez,
Hello.
what's your first name?
Christine.
Christine, welcome home.
Thank you.
Maria,
Here, Professor.
what's your last name?
Clemente.
Clemente, welcome home. Group number 9. Sheila Marie,
I'm here, Professor.
what's your
Anunciacion,
Annunciation, welcome home.
Thank you.
All right. Bolosin,
I'm here, Professor.
what's your first name?
Christiane.
You were not here yesterday.
No, I wasn't.
All right. Welcome home today.
Thank you.
We call it room every day now, so make sure you're here. Okay, you don't want to lose
Okay, thank you.
points for your attendance, okay?
Okay.
All right. Every point counts in time like this. All right. Galarudo. Alexa.
I'm here.
Okay. Welcome home. Okay. Anakin.
Here.
What's your last name?
Paez.
Right. Welcome home. How about Nathan?
Here.
Nathan, what's your last name?
Roseboro.
Roseboro, welcome home, Nathan. Okay. Raka,
Here, Professor.
what's your last name?
Tiu.
All right. Welcome home. Sestan,
I'm here, Professor.
what's the last name?
Winston.
Right. Welcome home.
Thank you.
Last group number 10. Okay. Alondra,
I'm here.
what's your last name?
Camacho.
Yeah. Welcome home.
Thank you.
Daisy. Is Daisy here today? Daisy's not here. Okay. Kimberly.
Here.
All right. Welcome home, Kimberly. What's your last name?
Lara.
All right. Mindy.
I'm here. Mindy.
Yeah, Mindy, what's your last name?
Shoal.
Yeah, welcome home.
Thank you.
Jessica. Jesse, are you here, Jesse? What's your last name? Welcome home. Okay, Christine.
Here.
What's your last name?
SYC.
Yeah, see. Welcome home.
Thank you.
Rija.
Here.
What's the last name, Rija?
Teodoro.
Theodora. Welcome home. All right. We're done with the roll call. Very good. It's working.
Professor,
Yeah.
I'm Shantae Brewer. I was trying to fix my audio on my phone.
Shante, bro. What group are you in, Shante?
I'm group 4.
Group 4. You were not here yesterday, right?
Yes, I was. It was just that my audio was messed up on my phone, and then I couldn't get it. Well, when I get in, I had to try to fix the audio.
What did I say yesterday?
Yesterday at the end of the class,
Uh-huh.
you said I remember that you was like, well, everybody is here now.
I said that.
Yes, at the end of the class.
Okay. All right.
Because I didn't get on to almost once you was almost done.
Okay. All right. And anybody else? Name I didn't call?
Professor,
Uh-huh.
I think Daisy, she said her audio is messing up, but she's here.
Daisy?
Yeah, from group 10. Group 10. Yes.
Daisy, you there now? Daisy?
Her audio's messed up.
But she's there.
Yeah, Daisy's here.
All right. All right. So anybody else? Okay.
Professor,
Uh-huh.
this is Jose from Group 7.
Group 7. Jose from Group 7. All right. Jose, what's your last name?
Serrato.
Were you here yesterday?
Yeah.
Okay. What did I say yesterday, Jose?
You told me the test is going to be an hour and a half.
Ah, well, how about that? You were here yesterday. Okay. Anybody else? Okay, so today we're going to, we still studying matter. Don't forget that. Chemistry is the study of matter and the composition. And matter has states. And we've seen those states in the chemical reaction. We'll talk about heterogeneous and homogeneous. The states appear. So now we're talking about these states. Yesterday we talked about the gaseous state. Today we're going to be talking about liquids and solids. Liquids and solids. How about that? All right. So let's get started. All right. Today's our last lecture. You're going to be prepared for the exam. All right. So we see that it says unlike gases. That means we're talking about gases already. We spent a whole time talking about gases. Unlike gases. That means they got something different that the gases do not have. So we want to see those differences this morning.
Professor.
Yeah.
I think Ezra's here, but their audio isn't working. They were here yesterday too, but their audio isn't working.
Who's that?
For Ezra Whitlock, I think it is.
What group is that?
I don't know. I think you said one of the first groups.
Well, let them speak for themselves.
The audio is not working for them.
But how do you know they're there?
Because we have a chat.
Oh, you have a chat. Okay, let's talk about that at the end of the class, okay? All right, so we have, we say, unlike gases, liquids do not respond dramatically with temperature and pressure changes. We talked about a PVT yesterday, PVT, and the number of moles relating to Avogadro. But here now we see that matter has these states, gases, solids, and liquid, but there's a difference in relation to these things here. All right, so we can study the liquid state and make 5 general observations, just like we made those observations yesterday with respect to the gases. Now, focusing on liquid state, here are some observation we need to pay attention to. All right, number 1, liquids have a variable shape. You know, we'll say something. We'll talk about variable meaning the subject to changing. All right, they have variable shape just like gases, but they have that in common. Variable shape, but a fixed volume. See different there? Variable shape like gases, but fixed volume. Gases are not fixed volume. That's different there. Liquids take the shape of their container, just like gases would do. Liquids usually flow readily. They flow readily. mean the viscosity is very small, so they can flow readily. All right. However, not all liquids flow at the same rate because of the key word there is viscosity. Make a note of that. Viscosity is the reason why all liquid do not flow. If you take honey, if you took your drinking water now, your bottled water, and ask the bottled water to take a race with honey. Say you put them down and say, who's gonna get there first? The bottled water gonna get there first because the honey has a higher viscosity compared to the bottled water. So that's something when they say here, liquid usually flow readily. However, not all liquid flow at the same rate because of viscosity. All right. Number 3, liquids do not compress. Gases will do that. Expand significantly. Gases will do that. The volume of a liquid varies very little as the temperature and pressure change. All right, the change is little compared to gases. Liquids have a high density compared to gases. All right. So we are familiar with gases. We've done gases yesterday, so now you should know. Liquids are about 1,000 times more dense than gases. We said what? 1,000 times mentioned yesterday in terms of air. Liquids that are soluble mix homogeneously. Soluble liquid, they have that property, okay, like dissolve like, that concept. So if we took organic liquid and put it in another organic liquid, it goes very well. When you talk inorganic and put it in organic, no, there's a line of demarcation. Liquid diffuse more slowly than gases, but eventually form a homogeneous mixture. So we can take alcohol and put alcohol in water. There's so many reasons why. Those reasons can be seen in Chemistry 66, and we can, if you come in with me spring, we can talk about that. The intermolecular bond is an attraction between molecules. Intermolecular forces. Big in Chemistry 66. Whereas the intra is the inter meaning, okay, inter meaning I'm traveling from California going to New York. That's inter. Okay? Within California, I'm coming from LA, I'm going to San Jose. That's within the same state, California, so that's intra. Intra is within. Inter is like coming from here to Nevada. Intra is within. Bond is between atoms in a molecule. All right. So some properties of liquids, such as vapor pressure, we talk about that, are determined by the strength of attraction between the molecules. All right? Some attraction between the molecules. So we see that molecular attraction. If you mix A and B, if A is more attracted to A than it is to B, then, you know, you're going to have the calculation will be very less. But if A is attracted to B and B attracted to A, then you know you have what we call Raoult's law. That's something you don't have to worry about. But just here, intermolecular bonds are much weaker than intra. The inter is weaker. All right, it's weaker going from here to Nevada. That's weaker. But within LA, it's strong. The strength, you know, within LA, which, you know, is stronger than going between Nevada and coming to California. All right. So we have the intermolecular force of hydrogen bonding, for instance. Hydrogen bonding is heavy in DNA in Chemistry 66. For those of you that are coming in, we'll be waiting for you. And the intermolecular force is the reason why the double helix in DNA. All right. So recall that a polar molecule, now polarity. So we say from intermolecular forces, 0.0 to 0.4, that's nonpolar. from 0.5 to 0.8, that's polar. From 0.9 to 3.3, that's ionic. So we see that information, you understand better in 6 to 6. So we see that, so with polarity, what is a polar molecule? So light dissolve light, a polar molecule dissolving another polar molecule. Non-polar molecule will create a line of demarcation, and there'll be no dissolving going on there. So we see that the uneven distribution of electrons in a molecule is called a dipole. Dipole interaction. Uneven distribution of electrons in the molecule. So you see when you have the HO bond, hydrogen bound with oxygen, the oxygen is more electronegative, so therefore it pulls the electron to itself, creating this pole, partial pole. So because where the electrons are being pulled from is partially positive, where they are pulling to are partially negative, so that creates the pole that we're talking about, dipole. So water molecule is a dipole, because what happened, the hydrogen, you have a hydrogen oxygen bond, and therefore you have this partial positive because oxygen is more electronegative compared to the hydrogen. So it pulls electrons to itself. That information will be discussed in detail in chemistry 6 to 6. So intermolecular attraction results from temporal or permanent dipoles in molecules. There are 3 intermolecular forces. Okay, dispersion forces of London by the gentleman named Fritz London. Fritz London, you know, take for instance, if you got something that is, you start something that has no polarity, and that let me use a good example would be a magnet, for instance. A magnet and a nail. One nail cannot pick up another nail, all right, by itself. But if I magnetize one nail, that nail can now pick up another nail. Okay, that's the dispersion forces we're talking about. All right, but when I remove the magnet from that one nail, the other nail will drop, and there's no magnetism going on. So dipole forces, what is a good example? All right, we have the hydrogen oxygen bond that I just mentioned, and between those two, the bond is covalent. We're going to be talking about bonding soon. It's covalent bonding between the hydrogen and the oxygen. All right, but therefore, the oxygen is more electronegative compared to the hydrogen. So it pulls the electron to itself. Where the electrons are going, it will be a negative environment. Where they're coming from will be a positive. The bond is not breaking, but it's just pulling the electron to itself, creating partial positive. And it's not true positive, it's not true negative. So that's polarity. All right? Dipole forces. Hydrogen bonds, for instance. All right? So we see that water has all 3. Water has a London forces. Water has dipole forces. But now, for anything to become hydrogen bond is a special force of dipole. All right? So how do we form hydrogen bond? Which element must be present? Fluorine must be present, oxygen must be present, nitrogen must be present for hydrogen bonding to take place. So we have a little acronym say FON. FON. All right? With the presence of fluorine, hydrogen bond can be formed. With the presence of oxygen, hydrogen bond can be formed. With the presence of nitrogen, so FON. So that's hydrogen bonding. All right? So we say DNA, the double helix is due to that, hydrogen bonding in DNA. All right. So we see dispersion for, let's talk about that. As a result of a temporal dipole. So with this introduction here now, when you get a 6 to 6, you say, yeah, I heard that before. I heard that. So take a look. Electrons are constantly shifting in a region they become temporary electron pole, slightly positive. While all this is happening in valence shell. Valence shell, all right, valence shell, the last energy level. All right. So we see electrons are constantly moving, you know, they're moving elliptically, shifting. So look at the top of that diagram. The top of the diagram, you see there's no charge anywhere. All right. So this creates a temporary dipole. So like I said, when I magnetize a nail, all right, then the nail look like this. Then this one is able to pick up the next one, pick that one up, because of the this is a dispersion forces that's taking place. Now take a look. Look at that one there. So now the positive can now attract the negative, and so on and on and on. So this is what we call a dispersion force, and was discovered by a man called Fritz London. So we can call it London dispersion forces. So dispersion forces, you know, take the name of the man who discovered it. So London dispersion forces. All right. So dispersion forces are the weakest intermolecular. So this is intermolecular forces. When between Nevada and California, the intermolecular forces can be dipole, can be dispersion, can be hydrogen bonding. That's the intermolecular forces. But the intra is that covalent bond. The covalent bond at the intra is stronger than the intermolecular forces. Dispersion forces are present in all molecules. So all molecules have London forces, all molecules. As long as it's a molecule, but all molecules do not have dipole, all molecules do not have hydrogen bonding, but all molecules have dispersion forces. All right, keep that in mind. Now, so the strength of a dispersion forces in a molecule is related to the number of electrons in a molecule. So we see that I say all molecules have it. All right, especially when you get to study organic chemistry, you detail in chemistry 66. We'll talk about when studying organic molecules, the dispersion forces will be stressed and why certain things cannot be dissolved in certain things and all of that. This has something to do with it. All right, now polar molecules. All right, we say well from 0.5 on to 0.8. All right, polar molecules have a permanent dipole. The dipole is permanent. All right, polar molecule, like water. Water has permanent dipole. The positively charged ends of polar molecules are attracted to each other. This is the dipole force. So take a look. Look at the diagram. All right, the strength of a dipole force is typically 10% of an intramolecular bond. So the hydrogen-oxygen bond is a covalent bond. So 10% of that HO bond is a dipole force. So the strength of the dipole force compared to the covalent bond, which is the intra, 10% of that strength is that of the intermolecular forces. That's what they're talking about. So dipole forces are stronger than dispersion forces. So take a look at that. You see that? The dotted line I show intermolecular forces are weaker. All right. The solid line will be the intramolecular forces. So that is it. So water molecule, when you think about water, we say water is H2O, right? But I tell you what, water molecule is not just H2O, there is a huge network. One water molecule hook up to another water molecule, hook up in a huge concern. All right? Because of the intermolecular forces, which is hydrogen bonding. Hydrogen bonding causes that to happen. All right, hydrogen bonds are a special type of dipole attraction. They're special because in order for that to happen in a molecule, there must be fluorine must be present, oxygen must be present, nitrogen must be present. That's why it's special. So you could have a dipole molecule, but if it doesn't have those features like fluorine, oxygen, and nitrogen, it will just be dipole, but it will not be hydrogen bonding going on there. All right. So hydrogen bonds are present when the molecule has what? The NH bond, OH bond, and the FH bond. FON as an acronym. Remember that, FON. So a molecule must, the nitrogen must hook up to nitrogen, must hook up to oxygen, oxygen to hydrogen, and fluorine to hydrogen. So we see hydrogen bonds are especially important in living organisms, DNA. DNA. All right, so you see that, look at the water molecule. So you see this one water molecule, it's hooked up to another water molecule by way of the hydrogen and the oxygen with that dotted line. The dotted line is the intermolecular forces between the two water molecules, and so on and so on, and just huge. It's a huge concern. So when we say water, it's not just H2O sitting there. It's a huge network. So that's something that you need to be mindful of. All right. Any questions so far? Regarding the intermolecular forces and intra? So it's being introduced here. Some of you probably heard that before. If you haven't, if you go to 66 in spring, you will say yes. We talk about that in 65. That's why 65 is a prerequisite for 66. All right. There are 4 physical properties of liquids that we can relate to intermolecular attractions. We talk present in the molecules. This is a intermolecular attraction now, meaning what? Weaker than the intra. So he had the 4 properties: vapor pressure, boiling point. I mentioned viscosity. When I tell you the bottled water and the honey taking the rays, the bottled water wins because the bottled water has less viscous compared to the honey. Surface tension. So when you put water in a glass, and you see the curve at the top, surface tension, because the molecule below what's on the top, the molecule at the top, the one below, they hook up to each other, but the one on the top got nothing to, they get hooked up to for the top, so therefore they form that curve and that surface tension. All right. Now you can see that better in a graduated cylinder, and we call that the meniscus. All right, so you got vapor pressure. So depending on what a intermolecular attraction is, this is how we're going to refer to the vapor pressure for that, comparing one to the next based on the intermolecular attractions. Boiling point. All right, so the boiling point of water is high compared to other substances that do not have hydrogen bonding going on. All right, so that's one of the things you're familiar with. So here we are. At the surface of a liquid, some molecules gain enough energy to escape. The intermolecular attraction at the surface, they gain enough energy, and then they escape of neighboring molecules and enter the vapor state. All right, the vaporization, when you boil it, this is what happens when you're boiling something. The molecule at the top, they try to pick up energy to take off. When they take off, they go into the gaseous state. And we know that these two terms, vaporization and condensation, they can equilibrate. If something that was vapor can go back down to condensation if you remove the heat. Something that will condense, you can if you apply heat to it, it can vaporize. So you see, they are, opposite of each other, just like freezing and melting. And just like we have a sublimation and deposition. Those terms we learned before. Sublimation, we know that when something comes from the solid state and it goes directly to the gaseous state without participating in the liquid state, that is what we call sublimation. All right. Now, when you lower the temperature, when you get it from the vapor back to solid state without going through the liquid state, that's deposition. And one good example would be carbon dioxide, which is dry ice will do that. Then you're familiar with that. And iodine crystals will do that. So we got the vaporization is the opposite of condensation, and melting is the opposite of freezing. And sublimation is the opposite of deposition. So all of these here are based on the intermolecular attraction of the neighboring molecules. All right, very, very important. The reverse process is called condensation. When the rates of evaporation and condensation are equal, the pressure exerted by the gas from vaporization molecule above a liquid is called a vapor pressure. Vapor pressure. So the pressure exerted by the gas molecule above that liquid that is boiling, that is being heated up, is called vapor pressure. All right? So we talked about gas pressure yesterday. And so let's take a look. We said the stronger the intermolecular forces between the molecules in a liquid, the less molecules are escaped into the gaseous phase. Like hydrogen bonding, dipole-dipole interaction. You know, the van der Waals, which is London dispersion forces are weaker. So any attraction between that takes place with the London dispersion forces, they fly away real fast because they are weak. Dipole, take a little while. Even hydrogen bonding is stronger. It's a special kind of dipole. So take a look. Let's take a look at table 11.1. Vapor pressure of selected liquids. Let's discuss that. So what are the liquids they selected? They selected water, propanoic acid, which is an organic acid. All right. Anytime you see COOH, that's called it carboxylic acid. But that we'll learn more in 6 to 6. Now, butyl alcohol. These are called functional groups. COOH, that's the functional group for alcohol in the organic phase. OH is the functional group for alcohol. So any organic molecule that has OH is considered alcohol. Propyl chloride. Chloride is another functional group. So ether is another one. You got one organic species. Oxygen is sandwiched between two organic species, make that an ether. So let's take a look at that. In this research, this person decided to study intermolecular attraction and the vapor pressure. The temperature is set at 20 degrees. This is our room temperature. So let's take a good look at that. So the approximate molar mass, that's the molecular mass, we've done that before. So how did they get 18? 18 meaning what? The weight of oxygen and the two hydrogen add together, you have 18 grams per mole. You're familiar with doing the molar mass, okay? Same thing for propionic acid. You got 2 carbon there, you got 2 hydrogen there, and then another carbon there, 2 oxygen there, and they put all their weights together, and they come out to be 74 grams per mole. All right, so this person doing the research was doing something that the weights are pretty close. He selected liquid that had the monomers are pretty close to each other. So he wanted to see, well, what big difference does it make if the monomers are far away from each other or close to each other. So they researched, this person decided to do just that. But they're all compared to water. Now, butyl alcohol, you got 4 carbon, you got 9 hydrogen, 1 oxygen, another hydrogen makes it 10 hydrogen. So the weight is also 74 grams per mole, which is the same as propionic acid. All right. So then the person look around and say, okay, well, what other molecule can I find that is so close to 74? And propyl chloride. So you got what? You got three carbon there. You got 7 hydrogens and 1 chlorine. Put them together, you get 7 to 9 grams per mole. That's pretty, all right? Then he found another one, ethyl ether. It has two carbon there, 5 hydrogen, then 1 oxygen, then 2 carbon again, and then another 5. You put them all together, you also get 74 grams per mole. So the person said, okay, I have selected molecules that either have the same molar mass or something close to that. So that's the research they're doing. So now, what is the intermolecular attraction? So you know water has all 3. Water has the hydrogen bonding, water has dipole-dipole, and water has the London dispersion forces. Okay, all molecules will have the London dispersion forces. You are told that. So all these molecules got London. They have London dispersion forces. Okay, so the acid got hydrogen bonding, got London, okay, and dipole-dipole. So this person doing this research selected things. So now we can see, okay, what is the big difference here? What caused one to be different from the other one? So let's see. So we see that water, the intermolecular forces for water very strong, because water has all 3 of them. Okay, very strong. And so is the organic acid, has all 3 of them. The alcohol also has all 3 of them. So now we have three molecules that have that intermolecular attraction are strong. And we got 2 of them that are weak because propyl chloride, ethyl ether do not have hydrogen bonding, okay? And so therefore they're weak. So take a look. Let's go to the column for vapor pressure. This is done at 20 degrees. So, you know, you don't want to have too much differences that are too far away, and you can't tell exactly what the reason why something is happening. So you got to make sure that things are pretty close. So the person did a good job here. So at 20 degrees C, the pressure, vapor pressure for water is 18 millimeter per mercury. Millimeter mercury. All right? That's the vapor pressure. At the same temperature, propionic acid is 5 mm of mercury. At the same temperature, butyl alcohol is 6 mm mercury. At the same temperature, propyl chloride is 300 mm mercury. All right? And ethyl ether is 450. So ethyl ether is weaker compared to propyl alcohol, and on and on. And so we see here, this study here can give us a lot of great information. So now, so you see how the person organized this study to see exactly what to look for. So here we go. Let's compare water and ether. All right. So water has strong intermolecular attraction because it has all three of them, the London dispersion forces, dipole, and it has a hydrogen bonding. And ether has weak intermolecular attraction. All right. So at 0 degree, neither has a significant vapor pressure. So there's no vapor pressure at 0 degree for water. There's none for ether. Fine. Both of them, no problem. But as we increase the temperature to 35 degrees C, ether has a significant vapor. You see that ether has a significant vapor. See that the gas is now, it blew up, the balloon. But water is still the same. It has nothing that's happening to the water. Because of the intermolecular forces for water being so strong, that you got to continue to heat. That's one of the reasons why you cannot subject heat directly. I mean, when you have organic compound, you cannot subject them directly to heat. You got to do it in a bottle, water bath or menthol. You cannot subject them directly to heat. Organic, because they're not strong. All right. So we see the ether is the organic molecule. At 35 degrees, look, the balloon is up. There's gas already in that balloon. The water does not. All right, because that's why it's so important to understand these properties, because when you're doing an investigation on something that you don't know, compared to something you know, this is one way you can tell which category to put as something that you don't know. All right, so here we go. Graphically, again, we can go to graph and find things. So graphs are very, very important. As the temperature increases, the vapor pressure of the liquid increases. Simultaneously, they go together, directly proportional to one another. Temperature and vapor pressure. So for different liquid, take a look. The graph is showing ether, which has which is an organic molecule, and going back there, we say ether 450 mm of mercury. Okay, so take a look at the graph. Look at ethanol. It's an alcohol. Alcohol, okay. This is an alcohol that people alcoholic beverage. This is an alcohol found in alcoholic beverages. Okay, any other alcohol in there can make you go blind. So ethanol is the one. So now this person took ether, took alcohol, ethanol, and use water, 3 of them, and compare them graphically. All right. So we see here the vapor pressure in mm of mercury versus the temperature. So when you look at the, if I wanted to know at 400 mm of mercury for ether, if I put a point there and drop that point down to the temperature line, I'll know exactly what the temperature is. Okay, if I need a temperature on a temperature line and put a dot there, go for a temperature line going up to the graph and go toward the left-hand side on the vapor pressure, I can find out what the vapor pressure is for that temperature that I just selected. So graphs are very, very, very important. At 700 degrees, the vapor pressure of 700. If I put a point there for the alcohol and drop that down to the temperature line, I can find out what the temperature is. So graphs are very, very, very important. Make things easier. All right. So the three values of ethanol, ether, and water graphically are showing us like how important graphs are, okay, to scientists. Now, so the number boiling point of a substance is the temperature at which the vapor pressure is equal to the standard atmospheric pressure. And that we refer to as normal boiling point. All right? Of a substance is the temperature at which the vapor pressure is equal to the standard atmospheric pressure. All right, as we saw in the previous graph, the stronger the intermolecular attractions, the higher the boiling point of the liquid. Okay, because the intermolecular forces is slowing it down for vaporization to take place. It's holding on tight. You got to keep heating for a very long time before they turn loose. Otherwise, you know, it's not going to get to that boiling point. A liquid with a high boiling point has a low vapor pressure. All right? High boiling point has a low vapor pressure. So let's see. Okay, a liquid. Let's go back. Go back. Okay, take a look at the table here. Okay. All right. So we got. You see the. So you know water has a high boiling point there. Okay. And so is the acid and so on, and the alcohol. Okay. So, and so then we see. So let's take a look. Let's talk about viscosity. Viscosity, I told you already, you know, will cause liquid to flow so slowly, like honey, molasses, you know, they are very viscous liquids, and so therefore they move very slowly because of the intermolecular attraction. So the viscosity of a liquid is the liquid's resistant to flow. Resistant to flow. Viscosity is the result of the attraction between molecules. If the molecules attract each other and the attraction is strong, then, you know, it's going to take a long time for it to flow. The greater the attraction between molecules, the higher the viscosity. So you have A is strongly attracted to A and less attracted to B. So you see, then it's going to, you know, the attraction is so high, viscosity would take place. Be very viscous. So the attraction between molecules at the surface of a liquid is called surface tension. That curve that I tell you, if you look in a glass and you see that curve from one corner of the glass to the next corner, it's because of that surface tension, the attraction. And no molecule at the top that can connect to the molecule to the top, so therefore it formed that curve. For an object to sink in a liquid, it must first break through the surface of that liquid. All right? The stronger the intermolecular attraction, the stronger the surface tension of that liquid. Okay. So let's go back to another table. We're going to use the same ingredients, same liquids from the previous table there, but we're going to study something different. When we studied this before, I go here, same liquid in table 11.1, but what were we studying? We're studying vapor pressure, all right? Same vapor pressure. But now this time, we're going to use the same liquid. The research is not going for vapor pressure. The research is concerned with surface tension. So everything else is the same, except for the last column, surface tension. The same temperature. What do you notice? Surface tension for water is higher than any other liquid there. It's 70. Why? Because water has what? Has all three of the intermolecular forces. All the molecules have London dispersion forces. All molecules got that. Okay? All right. But besides all molecules having that, all molecules do not have the non-dipole-dipole and the non-hydrogen bonding. But water has London dispersion forces, dipole-dipole, and London dispersion forces. So therefore, the surface tension for water is high. The difference here? That study was vapor pressure study. This is a surface tension study. Now, next in line will be the propionic acid. Okay, it's an organic acid. All right, it's next in line, and the alcohol next to the acid. And the propyl chloride, and then the last one is ethyl ether, is weaker. All right, we found ethyl ether was weaker in terms of the vapor pressure, and it's still the least for the surface tension. So these studies are very, very important, so that when you see something that you're not familiar with, if you see a liquid that you're not familiar with, you can do you can do surface tension study, you can do vapor pressure study, you can do all kinds of study, and compare them to the known. You ought to know what's happening. All right. So, any questions so far? Unlike gases, okay? So everything we've talked about so far, it was all about liquid. When we approach liquid, it's unlike gases. Now we come to solid, we also say unlike gases. We are comparing solid and liquid to gases. Very, very important. So unlike gases, solid do not respond dramatically to temperature and pressure. Same thing that we heard in when we were talking about liquid. Okay. Number one, solids have a fixed shape and volume. Everything about solid is fixed. So if I took a piece of rock and put it in a container, it would not take the shape of that container. It would not. But liquid will do that. Gas will do that. All right? Volume-wise, it will not take the shape of that volume. Unlike liquids, solids are rigid. They are rigid. All right? So they cannot behave like solid. I mean, they cannot behave like gases and liquid. Solids are either going to be crystals or they're not going to be crystals. All right, take ice for instance. Ice is a crystal. All right, from a crystal, and so crystalline solids contain particles in a regular repeating pattern. Okay, so we see so solids do not compress. This is in comparison to gases, expand to any degree. Assuming no change in physical state, temperature and pressure have a negligible effect on volume of a solid. You see? So we're talking about matter, and chemistry is the study of matter and its composition. And matter occupy, space, it has weight. And matter has states. So since yesterday, we've been talking about the individual states for matter. So there's a lot, when you study matter, there's a whole lot of things you can engage upon. Depending on what study you want to make. So you can pick a study and decide. Now, like this guy decided to do vapor pressure and a surface tension study. Surface tension study, I've done that before. All right. So we see that it is so important what aspect of the matter you want to study. So we see one important aspect is water. Ice, we mentioned that, is less dense than liquid water. Even though ice is made from water. But once we talk about freezing and melting, the opposite of each other. So once you solidify that water, so that a lot of things happen. So therefore, it becomes lighter than the water, density-wise, everything. All right. So that's something you need to realize. Solid do not mix by diffusion. Gases will. All right. So the particles are not free to diffuse in a solid heterogeneous mixture. All right. So these are properties that you need to pay attention to as you study matter. All right, very, very important. So this is how we can make decisions. Remember, we say in any scientific inquiry, observation is key to scientific inquiry. We observe, we hypothesize, we theorize, formula, all these things you do when you study matter. So here has some things that we need to remember about solid. There are 3 types of crystalline solids. 3 types. Examples of which are shown below. We have the ionic solids. How do you form ion? Go back. Again, think about your valence shell. The last energy level. The last energy level is the valence shell. And we say that when metals transfer electrons successfully to non-metal, that's ionic. To give you an example of sodium chloride. Sodium is in column 1, and everybody in column 1 has 1 electron in the valence shell. So it is not easy to go and collect 7 electrons to achieve the Goa octet. So it's easier to give away that 1 electron, making it +1. Now I assume the neon configuration. Look at chlorine. So the 1 electron that is sodium atom give away, it must go someplace. So chlorine is willing to accept this 1 electron to achieve its goal. Everybody trying to achieve the noble gas goal. So chlorine 17, we are one that has an argon configuration. So that's ionic. Complete transfer of electrons. So there are certain crystalline solids that are ionic solids. One good example of what you're familiar with is this sodium chloride. Sodium chloride. All right? Whenever you hear molecule, I tell you from the previous study, whenever you hear molecule, what type of bonding comes to mind? That's covalent bonding, where there's a mutual sharing of electrons. We'll be talking about bonding pretty soon. Mutual sharing of the electron. They share electron mutually. The water molecule, the bonding in water molecule is covalent in nature. Because the hydrogen share its electron with the oxygen, and oxygen share its electron with the hydrogen. So therefore, that relationship is they're co-ed, covalent, you know, they share, there's no mutual sharing. I mean, there are no transfer rather, there's no transfer, nothing is transferred there. They're mutually sharing the electron. That makes it covalent. So anything that share electron mutually will be considered a molecule. A molecule. So now, whenever we hear a molecule, start thinking what type of bonding goes on in a molecule. And that is a covalent bonding that goes on. Sulfur 8, for instance. Now, number 3, we talk about metallic solids, such as copper. All copper. Nothing else but copper. Crystalline network solids, such as diamonds. Diamonds, you know, the allotropes of carbon, graphites and diamond, come from carbon. All right, after burying the carbon for millions of years, they turn into diamonds. You know, they say diamonds are ladies' best friend. So ladies, you know how diamonds are made from carbon. All right, be nice to carbon. All right, so we see here, these are the 3 types of crystalline solids. You see? So the chemistry is huge. It's a huge undertaking. Because it's so, you can study, everybody out there doing different things, studying different things that they have interest in. They got to develop that interest in certain area and then put some time into that area and provide information to the rest of the people that are doing different things. So they got to know what you're doing. All right. So we see here's an example of a crystalline ionic solid. Okay. Composed of positive and negative ions. So you look at that, look at it, that structure there. The green are bigger than the other color, all right? Because the other color, they transfer the electrons, so they got smaller. The atomic size radius got smaller. This other guy received electrons, so therefore he got bigger. So all these things that, you know, you didn't remember them. So we see here now that the positive and negative ions arranged in a regular repeating pattern. Take a look. Just take one good look. They repeat. This one next, the green and the what's that, purple? The ladies no color. Over, right? So therefore, then the next time again, that green and the purple, and so on and so on. Just see that the pattern is unique and it's 3-dimensional. X, Y, Z from mathematics, 3-dimensional structure referred to a crystal lattice. So these are called a crystal lattice. In order for anything to happen, the crystal lattice must break. Other ionic compounds will have different crystal lattices. So we have 7 different crystals. There are some people that some chemists spend their whole life studying crystals. They make all kinds of crystals, you know. And you gotta watch those guys so that they fool you and they make crystals. This is a diamond, you know. They can do anything with crystals, you know. Because that's their specialty. All right. So a crystalline molecule comes to molecular solid. There are some solids that are molecule. All right. And so therefore, they're molecule because the bonding is covalent. Remember that. Ionic is the electron transfer going on there. All right. Covalent, molecule is covalent. Some solid can bind by means of covalent arrangement in a particular configuration. In sulfur 8, the molecules are arranged in a regular three-dimensional structure. All right? And those are in a hair business, they know some of suffer it. Other examples of crystalline molecular solids are table sugar. Now that you're going to learn more about when you do chemistry 6-6, but sugar there is an organic species. We're talking about sugar a lot, carbohydrates, okay? So we see here in water, when in our ice formation. So, but all of these are what? Molecule, because the bond formation is mutual sharing, mutually sharing the electrons, okay? Whereas in the case of ionic, there's a complete transfer of the electron. That's the difference between it. But it's all, we still study matter. Solid state matter. It's all about matter. So depending on what you want to study as an individual, you can't study all of it. Pick something and share with the rest of the people. So, metallic solid. It's pure, just one thing. Composed of metal atoms in a definite pattern. So that one pure thing, nothing else, but the atoms of copper, atoms of this. So a metallic crystal is made up of positive metal ions surrounded by valence electrons. All right?
Excuse me.
Yeah.
Can you go to the previous slide, please?
This one?
Yes. Okay, I got the picture. Go to the next one. Sorry.
All right. Okay, so we see here metals are good, they are good conductors because of this arrangement. So now, if you're going to build something or do something, that's one of the reasons why the study of chemistry is very, very important. We use material to do things, to build things. So what property these material got? That'll be good for what we're trying to do. You got to consider all that. That's one of the reasons why you have to study the material, because you want what you want out of that material. So you got metals are good conductors of electricity, because the valence electrons are what? Circulating in the valence shell, circulating constantly. And they are free to move about in the crystal. All right? They're there. It's neutral. In a neutral system, electrons are not being transferred yet. They're in the valence shell, and the electrons are moving about. This is referred to as the electron sea model. You like the sea. Look at it. You see it moving back and forth, rolling. If you go to Pacific Ocean, you sit there, you see the sea going back and forth, back and forth. So electrons are doing this, something similar. So all these things you gotta be mindful of. If you want something to conduct electricity, you're not going to take non-matter. Non-matter will not do it for you. So if you don't know chemistry, if you don't know chemistry to start to know what kind of matter you're dealing with, you take the wrong matter for what you want to use, or what you want to do. So if you know these things, you can get the right matter right away. If you want to do something, you go for the right matter. Diamond. Back to diamond. It's a special type of crystalline solid that has covalent bonds between large numbers of atoms. Large number of atoms. This type of crystalline solid is referred to as a network solid. You know, I told you that water molecule can form a network. So diamond is a three-dimensional system. You know, carbon that have been buried for millions and millions and millions of years. They call it allotrope of carbon. Graphite is softer than the diamond. The graphite we use in our pencil, so we see here, everything got purpose, got reason, what you need to use it for. All right, it's so important. So you got to understand what matter I'm dealing with, what matter I'm going to use, and what state that matter is in. What state that matter is supposed to be in before I use it? Should it be in the solid state? Should it be in the liquid state? Or should it be in the gaseous state? Which state is it good for what I'm trying to do? So all these things, these are research questions that you must engage yourself in order to do what you're trying to do. All right. So we see here, here's another table, table 11.4, general properties of crystalline solids. Ionic, the type of solid. Is it solid ionic? Is it molecular or metallic? All right. What are the general properties for ionic solids? It say what? High melting point. You want to do something with something that melts easily, then you're going to defeat the purpose. You want something that will take a long time to melt. So then you need to go for the ionic solid. Is it hard? Brittle? At least. All right? So what examples are those? Now, when the children of Israel were in Egypt, they were making bricks. They use straw in the brick making. Or you could use salt in brick making and make the bricks very hard. And calcium carbonate, magnesium sulfate. These are examples of ionic solids. We got a sodium is transferring electron, calcium is transferring electron, magnesium transferring electron. Sodium is in group 1, column 1, and calcium and magnesium are in the same family. So they're offering 2 electrons for the valence shell. All these things we study, when you're about to do something, which you are constantly making things. So when you engage in making anything, you begin to question yourself. What is the chemistry of this stuff here? What is this chemistry? So ionic solid is slightly soluble in water, Going back to the intermolecular forces again. Slightly soluble in water, conductor of electricity, when melted or in solution. So water alone cannot conduct electricity, but if you took some salt and put it in the water, the salt will ionize into sodium ion and chloride ion, and I bet you it can conduct electricity. You see? But if you took any other substance, like sugar, they put a dissolved sugar in water, it will not conduct electricity because the molecules are stuck together, there's no separation of anything going on. So you got to understand what material you're dealing with. You see? So, ionic material, they have very high melting point. They are high, they're brittle, at least. We count the molecular solid. They are opposite of the ionic solid. Low melting point. Generally insoluble in water. They have organic nature. Non-conductor of electricity. So we take what? We take copper wire. Copper wire will conduct electricity. What do we cover it with? We take rubber. You put we put a copper wire in a rubber. We can hold a rubber, and we would not be shocked because electrons are flowing. The electrons cannot get to the individual because the rubber is a molecular substance. So everything is good for something. But you got to know the chemistry of that something. It's very important. You all are going to be, many of you are going to be in healthcare business. All right, that's why you're taking this course. You're going to move on to 66. But you see, you got to understand why certain things work the way they do, why other things do not work the way they do, because of all these properties we're talking about. So we come from metallic solid where you have a neutral system where the electrons are circulating like a sea from the Pacific Ocean, ocean going back and forth, like the Red Sea, or this sea, that sea, Asian Sea. So low to high melting point. Malleable, meaning you can bend them easily, like copper. Silver, gold, malleable, ductile, conductor of electricity. If you want to conduct electricity, you look for the matter that can conduct electricity. Insoluble in most solvents. So before you play around any material, you gotta study the properties and the history of these things. The chemistry is so important that you know the chemistry of these things. You see? Now, so heat is a form we have 6 forms of energy. Heat is one of those. Heat is necessary to raise the temperature. Want to raise the temperature, we need heat. And change the physical state of a substance. We can change the physical state of a substance. Specific heat. So when we say specific heat, I mean every substance has a heat that is specific to that particular substance. Meaning that we can identify this substance by this special heat. Is the amount of heat required to raise, you take 1 gram, if you're going to do the research, look at different substances, 1 gram of each of those, take 1 gram each. Don't take 2 grams here, 3 grams here, 5 grams there. You're not going to know what's happening. But let it all be the same mass. That's how you do research. So that you know what is the variable, what makes the difference. Like we saw the two research that we just look at, certain thing got to be the same. So the thing that you're looking for will be the only thing that is different. So you can identify that as something. So you take 1 gram of different substances, and the temperature is the same. So you find, and then you identify the heat that is specific to that particular substance. Say, is the amount of heat required to raise 1 gram. So here's the substance. How much heat required to raise 1 gram of this substance? 1 degree C. We take the other substance, 1 degree C. So now we establish a specific heat for different substances. Because we took we took 1 gram of each of the substances to determine 1 degree how much heat required to raise it to that. So that's what we say specific heat. That heat. So when we talk about this substance here, when we see this heat, we know this heat, we know what substance that is. We go, all right, we already done our homework. Water is a reference, and its specific heat is, yes, water right here. The specific heat for water is 1.00 calorie per gram per degree Celsius. The water is used here as a reference. And now 1 gram of water. How do you do 1 gram of water? You take the bulk of water and multiply by the density of water you get in grams. But you can't weigh the water on the balance. Specific heats of ice and steam are about half that of a liquid water. The specific heats of ice, you know that we know the ice will float. We said that. And steam are about half, that's the same water we're talking about. Okay? But this is a different category, different physical state of water. The specific heat of ice, that means it's in a solid state. What is in a solid state? The specific heat of water as a vapor, steam, about half that of the liquid water, which is 1.00 calorie. You see that there? In a different physical state, same substance, taking 1 gram of the same substance in different states. We are finding out here that specific heat in a solid state, in a liquid state is different. And this is just water by itself. You could try and say, okay, well, I'm gonna take other substances and see what happens. What happens for other substances when they are in a solid state, in a liquid state, in a gaseous state? You could do all kinds of studies. You get a grant. All right. So we see here as the solid melts, the temperature is constant until all of the solid is changed to liquid. Okay, pay attention to that. So when you're doing a melting point in laboratory setting, mark the temperature at which the melting is initiated. And then you watch, keep your eye on it, keep observing until the whole thing has melted. Before you make that decision what the melting point is. You can't just something that is melting not complete yet and you say you establish the melting point. You gotta be certain amount. You gotta have certain amount. All right, the heat is the amount of heat required to melt. You hear that? 1.00 gram. So the mass has to be the same for everything you're trying to melt. So now the only thing that is different there, you're not going to worry about the mass, because you see, if you have 1 gram here, 5 gram here, 6 gram here, then you're going to go crazy and say, okay, maybe the melting point is because of that, because of the mass is different from this mass. No, they all got the same mass. So we're not going to worry about the mass now. You see? So we narrow it down to only one. The difference will now be one thing, the melting. So the complete melting. Gram of substance is called a heat of fusion. And this is required in your calculation. When you take something from solid state all the way to vapor state. All right? So these are the constant. So at this point, 80.0 calorie per gram, temperature is constant throughout. Temperature is constant. When you're doing a thermodynamic study, for water, the heat of fusion is 80.0 calorie per gram. Per gram, 1 gram. Called the heat of fusion. When a liquid changes to a solid, the heat change is the heat of solidification. It's the same heat just going from one point to, so therefore we see that we're taking out the heat that we're putting into melting. We're putting the heat out. We're trying to make us, so when you take the same, use water as an example, putting in the freezer. It will solidify to ice. So the value of the H of fusion is the same as the value of the H of solid. So it's just, the heat just going back and forth. You put it in something, you take it out of something. All right? So it's not different heat that you're dealing with, the same, you're just moving it back and forth. All right. As the liquid vaporizes, the temperature is constant. You have a liquid water, liquid for instance, let's say water, and it began to vaporize. Vapor pressure we talked about earlier. Again, vapor pressure. It began to, the boiling point is coming now. When the boiling point takes place when the atmospheric pressure is equal to the vapor pressure. That's how boiling comes about. All right. So at sea level, let's say sea level. The other day you did something that above sea level. So as the liquid vaporizes, the temperature is constant until all of the liquid is changed to gas. So while the liquid is changing to gas, you don't record anything. You wait. Record the initial time the bubble start. That bubble, the first bubble is very important in chemical engineering. That first bubble. All right? So that the first bubble start, you pick up from there and wait and see how many bubbles are formed after that first bubble. All right, so now we see that the amount of heat required to vaporize 1 gram now. We're working with 1 gram of a substance called the heat of vaporization. We're going to vaporize 1 gram of the. For water, that value is 540 calories per gram. Temperature is constant there. Fusion 80.0. Temperature is constant. When you're doing a heating curve problem, which I know you guys have in your homework. This is how you do a heating curve. Now, when the temperature is constant, it's plateau there. It's plateau, it's flat. When you're doing the heating curve, where a plateau, the temperature is constant. That's what the flatness stands for. Then when it starts rising, then you got away from that plateau region, you go into a different substance now. And the temperature begin to go up. Then it plateau again. Plateau when you go into the gaseous state. Very, very important. These concepts are so important. Now, some companies, some organization, this is how they make their living at doing this kind of stuff. That company will, all day long, they're looking at a heating curve, doing all kinds of stuff. All right? So you got vapor and condensation, opposite of each other. If you remove that heat, the vapor, you go back down in condensation place. As I mentioned earlier, that's what I'm doing right now, making my mouthwash from the vaporization and condensation process. All right, so therefore, some substances convert directly between the solid and the gas phases. All right, some substances convert directly between solid and gas phases, and we call this now. We already talked about freezing and melting. We talk about condensation and vaporization. So now we're about to talk about sublimation and deposition that I mentioned earlier. In this process, one state is omitted. For some reason, matter has that property that will cause something not to go from solid to liquid to vapor. It will escape that liquid state. So there are certain substances will behave that way, have that behavior. So if you're doing some job and you want something like that, you go for those substances. You know what? If you don't want to have something to go to the liquid state, you find things that will not go to the liquid state to make that vapor. You want vapor to be made, and you want to use that vapor for something else, but you don't want liquid involved. So you find a material that can do just that. That's the purpose of studying matter and the different properties of matter, different states of matter. It's so important. So is the process of a solid changing directly to a gas is called sublimation. Carbon dioxide, dry ice will do that. Dry ice will do that. Iodine crystal will do just that. Carbon dioxide is dry ice. If you didn't know that. Iodine crystal. Now we do this in a setting, in a normal setting in the lab. We do this iodine, and the students are so fascinated by that. They all line up to see it. But this is one experiment that I do, the student don't do, or other teacher, when they teach that class as well, do the same thing. We do it and we let students come by and observe. First, we take the crystal, put in the iodine, put in a beaker. You have a picture of it. You see that picture. Put in a beaker and then take the evaporating dish, cover the beaker with it, put ice in the evaporating dish. So as you heat up the crystals, the crystal will sublime. They go from solid, go straight to the gaseous state. But then as they go up, when they hit the bottom of the evaporating dish, there's ice inside there, so the ice begin to cool the vapor. So now the crystal now, deposit at the bottom of the evaporating dish. Fascinating. And students see that, oh, this is nice. Oh, I've never seen that before. But you're not going to get to see that. So I'm explaining to you. All right. So now that is what we call sublimation and deposition. When you put the ice inside the evaporating dish, it cools the vapor, and the solid deposit. So that's deposition. We're depositing the solid at the bottom of the evaporating dish. All these things, people are engaged in studying matter every single day, doing different things. You take the chemistry of interest and do business with it. and do something with it. That's how chemical industry are established. Just for this thing we're discussing here. Somebody said, well, I like this one. I'm gonna open up a factory, open this, and create jobs for other people. So here's what I've been telling you about. We can grab the amount of energy required to change the temperature and physical state of a substance. This is all physical. It's physical because we are not breaking any bonds. From the previous study, we said that to be chemical, you gotta break old bonds and make new bonds. But in this process, when we play with water like that, making water into ice, evaporating, melting it and making liquid and then back to vapor, it's still H2O. We haven't changed anything, so we didn't break any bond. So it's all physical. But when we start to break the bond, making hydrogen gas by itself, oxygen gas by itself, that's entirely two different things we got from that water molecule. So therefore, that's chemical. All right, so the heating curve. So we call this a heating curve. This is the heating curve for water, the heating curve for everything. There's some industry all day long, they do heating curve. Some people go to work, they tell their family, I see you this evening. They go and do this. This is how they do. They do heating curve. Heating curve all day long, heating stuff. Make a living out of that. So as energy is added, the temperature increases and it changes the physical state. You hear that? We want to change the physical state. What are the physical state? Solid, liquid, and gas. One state we're not talking about here is plasma, which is bigger than all states. Well, this course does not deal with plasma here. Discuss plasma. We're not liquid, solid, and gases. So we see that, look at a crystal there. See the solid there? We have a temperature. We have the additional heat. All start from zero. Where the solid is situated, that's zero right there. So now we begin to do apply heat to the solid. We apply the heat, so the heat goes up. I mean, it's going up. See where it says fusion? See that plateau there? Fusion and solidification. All right there. It's plateaued and the temperature is not changing. The temperature stay put. This is a block of ice now. Temperature remains the same as the ice is melting. Ice is melting. When it get right there, you see that little break there? That means temperature is about to go up. It's because all the ice is melted. Everything now is in the liquid form. So liquid form, and the temperature is going up. It's going up. The temperature continues to go up. And they get to another plateau. The precision condensation at that plateau. The temperature is not changing. And the liquid will stay liquid form until all of it is changed, and from that point on, it begins to rise to go up to the gaseous state. That is the heating curve. So we can reverse this. We can go from the gas going back down to solid, going back. So we're taking the heat out, all the way going back down, we're taking the heat out. So when you put something in the freezer, you are taking the heat out. Taking the heat out. If you get it out of the freezer, You're exposing heat to it, back and forth. No bond broken here. It's all physical. And I'm sure you got some problems there that relate to this right here. Now, in a normal situation, if we were in a regular setting, I usually give a problem like this for different substance. It'll take you a long time, so many steps to do. But we're not there, so I'm not giving it to you. So this is what we're talking about. This is a heating curve. All right? Any questions so far? Now, we can use the heating curve and heat values for water to calculate how much energy is required to change the temperature of a sample of water. A sample of water. We have a sample. Sample simply means comes out of a population. That's what sample is. A sample of water. The amount of energy required to raise the temperature of a substance is calculated using the following formula. So the heating curve. So the specific heat times the change in temperature. Whenever there's a rise, so you got to find a specific heat of that substance. Multiply the specific heat by the change in temperature. You've got a question saying that what is the heat is going to be in calorie or joule, whatever you want it to be. All right. So specific heat has unit. So things will drop out. You have it in calorie or joule, whatever you're doing, times the mass of the sample. So that is what we call all right. The amount of energy, and Q in this case can be, we can designate T to be Q. All right. So we can call it, we can generate a little formula. You might need a formula for your calculation. Q equal to MC delta T. Delta T is the change in temperature. So you can say the delta T is equal to T2 minus T1. Or it depends on the textbook. It could be TF minus T sub I. All right. The M here is the mass. It doesn't change. All right. And the C is the specific heat. So when the temperature is going up, you apply this formula, MC delta T. So when the plateau, then you have what? Q there is M L F. F is the fusion, latent heat of fusion, the mass times latent heat of fusion, or when a plateau Y is trying to form vapor, Q is equal to ML all right. Condensation, okay. So the latent heat of fusion, and so L sub V, which is vaporization, we can use that, mass and LV, mass and LF. So they combine all those heat units. All right. So do you understand that when the temperature is going up, you have to multiply the mass times the specific heat times the change in temperature, which is delta T. when the thing is going up. When it's plateau in the fusion area, is the MLF, fusion, mass times latent heat of fusion. When it's a plateau from liquid to going toward a vapor, is mass times LV, which is latent heat of vaporization. All right, we were given those values. Let's go back to water. All right. Okay. Look right there. The amount of heat required to vaporize 1 gram of substance is called so and so. So for water, the LV is 540 calories per gram for water. The LV. All right. And the LF is 80.0 calorie. All right. It's 80.0 calorie per gram. LF. That's the heat of fusion. So you take the mass of that and multiply by that. All right, so here's an example. The heat necessary to raise the temperature and change the physical state of a substance. Okay, we'll talk about that. Okay, let's go here, right here. Okay. Let's take a problem. Here's a typical problem. Let's take a look. How about I get involved in this problem? The question here is how much energy is required to raise 25.5 grams of ice at this temperature to steam. We're taking it to steam. This temperature is below 0. And we're going from negative 5.0 degrees Celsius. And we're taking it to steam at 100 degrees. So that's the variable right there. The mass is not going to change. 25.5 grams of ice. Okay. Looking at a heat curve for water, there are 4 regions. Here's a heat curve for water. Look at the four regions. All right. 1, 2, 3, 4. 4 regions. You see the 4 regions there? Okay. You begin to heat up something. It's melting. And the heat of fusion is 80.0 calorie. Okay. So there's a 4 region there. Go back to the problem. Look at the heating curve for water. They have 4 regions. Number 1, heating of solid ice from negative 5.0 degrees C. You got to take it to 0 degree. You guys below 0 degree. Okay. What does that step require? Q, which is designated for heat, that step require, the formula to use there is Q equal to MC delta T. Q equal to MC delta T. First, number 1. You need a formula for that. Melting of ice at 0 degree, a plateau, nothing changing. What you need Q is equal to what? MLF. MLF. Okay. Step number 3, heating of liquid water from the 0 to 100. What is required? What formula will you use? Anybody, can somebody tell me what formula will you use there? Anybody? I've given you 3 formulas. Which one will you use as step number 3? Maybe I should start calling some name. Since I can't get a volunteer. Okay, Riley? Riley?
Yes.
What formula will you use as step number 3?
I honestly don't know.
Okay, let me find somebody else. Group number 2. Christina. Constable. What formula will you use as step number 3? Okay, let me go back to Riley. What are the formulas I gave you? Can you read them back to me? Huh? Okay. Who are you? Jessica? What group, Jessica? 10. All right. All right, Jesse, go ahead. What's the formula I gave you? Okay, just tell me the formula. Q is for heat. Yeah, Q is equal to MC. Write it down. Yeah, MC delta T. That delta T is a change in temperature. Everybody should write it down. Q equals MC delta T. That's one formula. Another one is Q equal to MLF. Formula number 2. The next one is Q is equal to MLV. Okay, do you all have the 3 formulas?
Can you repeat them again, please?
Okay, Q, which is heat, Q stands for heat, equals to MC delta T. M for mass, C is a specific heat, and delta T is a change in temperature. Delta T can be T2 minus T1 or TF minus T sub I. Depends on the textbook you're working with.
Okay.
Everybody got that? I hope you wrote down. It'll be required of you for the exam. Okay, so Jesse, you correct for step number 3. Congratulations, you got that one right. All right, so we'll celebrate you, Jesse. Now, step number 4. Rebecca from group 6. Step number 4, which formula will you use? Is Rebecca there, group 6? India?
Hi, Professor. I'm not sure. I'm actually looking in my book right now.
Is it Rebecca talking?
No, this is India.
India, okay.
Yes.
So which formula will you use? Do you have all 3 formulas I gave you, India?
No, I'm still writing them down.
Okay, let me give them to you again, okay?
Okay.
Q is equal to MC delta T. Q equals,
Okay, I got it.
you got it?
Yes, I did.
And the other one is Q equal to what? MLF. And the other one is Q equal to MLV. Of those three formulas, tell me which one will you use for number 4?
I'm not sure. I mean, I could take a guess. I'm
Right.
not sure. Maybe the first one you gave me. I don't know.
Okay, now, let me go back. Whenever there's a change in temperature, delta T is required there. You see that? Do you see change in temperature in 2 and 4? In there?
Yes.
No, do you see change in temperature?
Yeah, I do.
No. Look at 2. The temperature a constant at what? It stays at what?
I'm lost. I don't know.
At 0 degrees
It
Celsius?
stays at 0 degrees Celsius. It's not changing. Take a look.
Okay, I see it.
All right. Take a look at 4. You see any change going on there?
Yes.
What do you see the change?
It's from now it's at 100.
What is that changing? Any change going on?
Yes.
No. It stays at 100.
Oh, okay.
You got it now?
Yes, I got
Look
it.
at number 1. Do you see change going on there?
No.
Number 1. Look at number 1.
Oh, yes.
Yes. You see that now?
Yes.
Because of that change, the formula you're going to use is Q equal to what? MC delta T. You see that now?
Yes.
So look at number 3. Jesse just told you that there is a change going on from 0 to 100. So therefore, the formula to use is what? MC delta T. Everybody see that? Who's not getting it? Anybody there not getting it? I don't want to leave this until you get it.
I have a question, Professor.
Yeah.
What does the delta T stand for? You said it was like
Change. The delta
T1.
is change. Delta. Delta stands for change.
Okay, but
It's a little triangle. So
and then what's the other way to write it? There was another way to write delta T.
Yep. You put a little triangle. You put a little triangle, right? And then after the triangle, you put T after the triangle.
Okay.
So the other way now, what does that mean? Delta T is equal to what? T2 minus T1.
Oh, okay.
You see it now?
Yes.
Or TF minus T sub I, depending on the textbook.
Okay.
You got it now?
Yes.
So
And then for the other equations, what does the LF and then LV stand for?
Latent heat. Where it's constant, doesn't change.
Okay.
Yeah. Fusion. F stands for fusion and V stands for vaporization.
Okay.
You see that now? Everybody?
Yes.
You have that? Okay, now yeah, exactly. So no, because all you gotta write is the mass time that vaporization, which is 540 calorie per gram. That's LV. And LF is what? 80 for water now, 80.0 calorie per gram. In place of LF, if it's water, depending on what material you're working with. You got it now? Everybody? Anybody there who hasn't gotten it yet? This is a class participation that you're supposed to get a grade for. You're supposed to participate. So if you don't get a grade for participating, then don't blame me because it says there, it says.
Excuse me.
Yeah.
Excuse me,
Yeah,
sir.
go ahead.
May you go over the formulas again, just so I can finish writing it all down?
Okay, all right. Who's that? Who's talking?
Chanel Marshall.
All right, Chanel. Okay. The first formula, right?
Right.
When the temperature is changing, is Q equals to MC
Delta T.
delta T.
Okay.
Okay? Where delta T is T2 minus T1 or T sub F minus T sub I.
Okay.
Okay?
Okay.
Soon as you see change your temperature, that's the formula you use. Okay?
Okay, perfect. Thank you.
Let's look at number 2, step number 2. It's melting. The solid is melting. It's in the melting stage, so it's plateau. Okay, you see that now? Let me see if I can take you there. Okay, you see that? Where's the fusion? Look at the diagram. You see the diagram? Are you watching the diagram?
Yes.
You see where it plateaued there? Where you see fusion, the word fusion, you see fusion there? Solidification, fusion?
Yes.
That
Yes.
area, the temperature is not changing. So that's a M times LF. You see it?
Okay, I get it.
You got it now?
Yeah, so when there's a change in temperature, you use Q equals MC delta T. But
Very
when,
good. Now, who's talking?
Anakin.
Anakin, very good. Hello?
And when it's in a plateau, like when it's just flat, like and for example, if it's fusion, it'll be Q equals MLF.
Right.
And vaporization in that plateau up by the top, it would be Q equals MLV.
Very good. Let's celebrate that. You see that there? So that's what's happening. You're going to combine all these heat. So you see, when the fusion is going on, it's a mixture of what? Solid and liquid, right? It's where the fusion is going on, it's melting going on. It's not all liquid yet. So the temperature is constant there. Everybody see that?
Yes.
Okay.
Yes.
Now, you see that point where the things start going up now? It's all liquid now. See it rising, going, going. When it get over here, it plateau again. That means it's what? It's a mixture of what? Liquid and gas, right? Vapor pressure, liquid and gas. Until all the liquid is gone, then all gas and so forth. So at that point, you multiply using 540 calorie for L sub V. Okay? All right. So, any question, anybody? Is it clear so far?
I had a question, Professor. You mentioned that for delta T, that's when it's T2 minus T1, correct?
Right.
Okay.
Or TF minus T sub I, depending on the book. The T's are actually final. T2 is the same final temperature. T2 is the final temperature. T1 or T sub I is the initial temperature. The temperature you start out with before things start, going on the way they are, right?
Professor, what was it again? Was it TI?
TI is the initial temperature.
Okay. Thank you. Yes.
And the T sub F is the final temperature. You got that now?
Yes, thank you.
Nice to meet you.
All right. So let's find the problem. So now here's the problem right here. So we want the total energy at each of those levels. We want the total energy. The total energy is the sum of the energy in steps 1 through 4. Okay? Total energy. That's our goal. So we're going to take some time to do this. So total energy, okay, so therefore we see that at the first stage, what are we using? Which formula are we using? Q equals to what? MC delta T, right? Ever see that?
Yes.
Okay. The 25.5 gram, that's the M. The delta is a 0.0 minus 5.0 C, and the 0.50 because you see, they told you that even though ice is made from water, or ice and steam, the specific heat is half that of water, which is 1.0. Remember that? So the specific heat of the ice is 0.50 calorie per gram times degree C. You got to put in all the units so you see. When you put in all the units, you notice that the C cancel with the C. The gram cancel with the gram, and the only thing you have left is calorie, which is heat unit. Ever see that? In problem number 1? So now you got what? You do the math, you get 64 calories in the first step. Any question on that? Everybody, you got it? So step 2, where it plateaus. No temperature change. The temperature is not considered in this calculation. So which is the M, Q equal to M, LF. And LF is 80.0 calorie per gram. And M is the same, 25.5 grams. So the gram cancel, you have calories. So at that second level, you got 2,040 calories involved. Melting the whole thing. Melting it all the way to liquid. Everybody see that? And it's all in liquid now, so therefore the temperature will change. So from 0, it changed. 0 is the initial temperature. So it's changed from 0 to 100. That's delta T right there. So 25.5 grams times that, delta T. The specific heat of water is the same throughout. This is water now. We're in water now, so it is 1.00 calorie per gram. When it was ice, it was 0.5. When it's steam, it was going to be 0.5 as well. Okay, so therefore, there's a temperature change in step 3. So now we got 2,550 calories of heat generated from that step 3. All right, so now it's all steam. It's plateau there. Where is plateau? For vapor, 25.5 grams. The LV is 540 calories per gram. So now the gram cancel, we have calories 13,800 calories. So it's everything in calorie now. So what is the total calorie? We done added 64 plus the 2,040 plus the 2,550 plus the 13,800, and that total will give us 18,500 calories required to take ice. The amount of ice, 25.5 grams now. Not all masses, but this particular mass of ice. 25.5 grams will give us 18,500 calories. Everybody see that? Now, when you're doing the homework, this is the way the homework problem is supposed to be done. If you have a problem, a homework problem like this, I want to see all the steps, all the units in the problem, making sure the desirable units are dropping out and the desirable unit remain, which is calorie. If they actually to change it to joule, the equivalent, you use that. All right, any questions so far? Anybody? This is water. Different substances got their own heating curve. This is the heating curve for water. All right. We got it okay, everyone, right? Got it good? Okay, let's move on. Water has a bent molecular shape and a bond angle. Okay, you'll see more, we'll talk more about this in chemistry 66. All right, bond angles and molecular shape. In water, each of the two bonds has a dipole, making water a polar molecule. The H and oxygen. All right, so that's a polar. So therefore,
Professor? Professor, oh, okay. I'm so sorry. This is Christina. I was just testing because my mic. You called on me earlier, but my microphone wasn't working, so I got it to work. I'm sorry.
Okay, all right. I'm glad.
Okay.
But did you understand what I've done with the problem?
I did. Yeah. Thank you so much.
Okay, you got it?
Yes. Thank you very much. Sorry about that. Sorry to interrupt.
Right. So here we go. In many areas, water has lots of dissolved minerals. Depending on where you are, leading to high concentrations of ions. We hear ion meaning what? Think about a valence shell. Electrons are leaving, being transferred, making ions. This is referred to as a hard water. The water can be hard water. When the water is hard, it takes a lot of soap because it doesn't make foam easily when the water is hard. It is often not suitable for use in agriculture or drinking. Hard water is not. All right? The water is purified in the water softener by exchange. Water softener is exchanging the cations and anions for hydrogen ions and OH ions. So this is some people's business. Some organizations they set up plant just to soften water, and people buy that soft water. All right. Water is one of the few substances that is less dense as a solid than as a liquid. As water freezes, the hydrogen bonds, the intermolecular bonding, which is hydrogen bond, organize the water molecule into a three-dimensional structure, where the molecules are further apart than in the liquid. Liquid water has a density of 1.00 gram per milliliter, while ice has a density 0.917, because ice is lighter than that water. It floats on water. All right, so these things are things you got learned. Here's water has unusual melting and boiling points because of these intermolecular forces that we're talking about. London dispersion forces, you got the dipole and the hydrogen bonding. All right, so this is due to the hydrogen bonding that is present in water, but not present in H2S. You know, H2O, we say FON, for hydrogen bonding to take place, fluorine, oxygen, and nitrogen must be there. But H2S, you don't have that happening, so therefore, we're not hydrogen bond. All right. So we have water can undergo an electrolysis reaction to produce hydrogen oxygen. This is a chemical reaction. So I mentioned earlier that water, cannot conduct electricity, but when if you put something like sodium chloride, like salt in water, it can happen. So it can conduct electricity. This is a chemical reaction. Okay. All the other things we talk about water are all physical, but this is chemical. Because now we got what? Different substances. We got hydrogen and we get oxygen. Balance the equation. We see that's something we learned from the past. Water reacts with active metals in column 1, for instance. All right, to produce hydrogen and then metal hydroxide. So potassium is in column 1. You take a potassium metal and drop it in water. And then so you form this, you make hydrogen gas and you make potassium hydroxide. That is a chemical reaction. Water reacts with metal oxides to produce a base. So therefore the oxide of any metal, you throw that in water, you get a base. So that's another chemical reaction going on there. Water reacts with non-metal oxide to produce an acid. So you see, calcium oxide is a metal oxide. Metal oxide will give you a base. The carbon dioxide is a non-metal oxide that gives you acid. So non-metal oxide will give you acid. Metal oxide will give you a base. Take a look at the two reactions. All right. So now we see water is obtained as a product in several types of chemical reactions. We talk about combustion reactions. We talk about neutralization reaction. We talk about dehydration reactions. And so take a look at the combustion reactions. So you take an organic compound like C3H8, and this is a homogeneous reaction. We spark it up with oxygen, and what happens? We get carbon dioxide and we get water. The amount of water we get is based on the size of the carbon compound we're dealing with, hydrocarbon. So here's the next one, the alcohol. We treat it with oxygen, spark it up, we get carbon dioxide and get water. This is a combustion reaction. This reaction, now, one thing that I'm mentioning here, plus energy. And this energy can be used to generate electricity. Okay, can be used, to make electricity, but they left it out. But it's supposed to be there. Neutralization reaction, acid and the base. We come into that. That is the last lab you're going to be doing. But to end this course, neutralization reaction, you get salt. Whenever acid and the base react, you get salt and you get water. Always. Dehydration reaction, taking water out of the system. You see more of that when you do 6 to 6. More of this thing. Water is driven off from hydrate by heating. So we have crystals like the water is embedded in that crystal. When we heat up that crystal, the water disappears. Here's an example, hydrate. This hydrate will be on your examination. So let's pay attention to this section right here. It's an hydrate. And how you're going to be?
Excuse me.
Yeah?
Excuse me. The video, it keeps dropping. The video keeps dropping. The video keeps dropping and disconnecting.
Oh, yeah? But can you hear me now?
I can hear you, yeah, but it just keeps dropping, and I don't know if you noticed. Because I come back and the slide is different. So.
Oh, really? No, I don't notice that.
It's working for me. So it might be.
Oh, it might. Okay. So try and do something, not for everybody. Okay, so that means do something on your side. All right, so a hydrate. Whenever you see the word hydrate, meaning water is embedded in a system. A hydrate is a crystalline ionic compound that contains water. So this hydrate, you're going to have hydrate on your exam. So make sure you know more about hydrate. It's on your study notes. The dot indicates that water molecules are bounded directly to each unit of hydrate. That dot. So you got 5 water molecules bounded to each of those, crystals. Heating a hydrate drives off the water and produces an anhydrous. D-R-O-U-S, meaning there's no water there. D-R-A-T-E means there's water in there. That's the difference. D-R-O-U-S, there's no water. D-R-A-T-E means that you got water in there. Okay, so now this is a copper sulfate pentahydrate, meaning 5 hydrate, 5 water molecule. So now you see that little delta? That's the delta you need to attach to the T for the delta T. This is how the delta should look. That little formula plus T to be a delta T. All right. So we have this crystal got water in it. We're going to remove the water by heating it. So when we heat it up, that delta meaning heat, the heat is the catalyst. We heat it up, copper sulfate solid. We have no water there now. All the water gone. So the water is in the gas, got back to liquid form. So we got the water, okay. Heat it up, gasified, then back to liquid. All right, so this is the stuff we're going to be doing on the exam. Okay, so let's take a look. So bottled water is a very large industry. Everybody trying to sell water to everybody. Water from our home faucet is tap water. It's tap water, it has all kinds of minerals in it. So that water there, if you pass current through there, the light bulb will light because there's mineral in that water. Tap water that has been processed by distillation or deionization is purified water. Or when we distillate tap water, take out all the minerals from there, that's purification, and they cannot, conduct electricity. Spring water is obtained from natural underground springs. Some people are in that business. In most cases, bottled water has lower purity standards than tap water. Okay, so they try to take out some stuff. All right. There are 3 types of intermolecular bonds we need to be concerned with here. Dispersion forces. London dispersion forces, all molecules have that. Dipole forces, some have it, some not. Hydrogen bonds, some have it, some do not. Dispersion forces are the weakest, and hydrogen bonds are the strongest. Things to talk about today. These intermolecular attractions affect the physical properties of substances. So you got to pay attention to the intermolecular forces of all materials out there. All right. There are 5 properties of liquids that are affected by the intermolecular bonds. Vapor pressure decreases as intermolecular forces increases. Vapor pressure decreases as intermolecular forces increases. Boiling point, we saw on the charts, we saw today, boiling point increases as intermolecular forces increases. Viscosity increases as intermolecular forces increases. Surface tension increases as intermolecular forces increases. So pay attention to that. Vapor pressure decreases. as intermolecular forces increases. All of these things, when you increase intermolecular forces, something happens. You need to pay attention to what happened to material, to substances, when intermolecular forces are increased. That's one way to look at it. All right. Now, there are three types of crystalline solids. They can be ionic, when the valence electrons are gone, being transferred. They can be molecular solids when they are mutually sharing the valence electron. Metallic, we have the electrons are going around, circulating. That's like a sea. Energy is required to raise the temperature of a substance. Water displays many unique properties due to the presence of strong hydrogen bonds. All right, so that is the end of this chapter. And do you have any question? So you're now ready for the exam.
I have a question about the exam.
Uh-huh.
Is it going to be on Canvas?
Yeah.
Okay.
The exam can be, in fact, Canvas is ready.
Right, but if it is on Canvas, will it be under the quizzes or the test section that is open?
Yeah. But where it say quizzes, whatever it say test, whatever, go to that session. Mm-hmm. Tomorrow, let's see.
Please.
Or we can do, okay, we can take, tomorrow is the 30th, right? So we can use that for review time, yeah. Okay. All right.
Thank you.
And then, then later on you can start a test, okay? All right, so I have to call roll too.
Professor?
I'll call roll tomorrow, okay? If I'm gonna do that, I'll call roll, so be prepared for roll calling. Yeah,
Professor?
Yeah.
I was just wondering what time the quiz or the exam would open tomorrow.
The thing is, let me see. 11:59. Yeah. 11:59.
11:59 p.m.
Yeah. Mm-hmm.
Oh, okay. And you said that it closes on August 4th, you said?
Yeah.
Okay.
Yeah.
Thank you, Professor.
All right. Any other questions? So tomorrow we meet. So save all your questions, right?
Professor, I have a question about tomorrow.
Yeah.
Okay, so there is no lecture, but is there a lab for people who have lab for you?
Yeah, we have lab tomorrow. Yeah.
Okay, thank you.
Okay. Any other question?
I have a question, Professor. For the homework, is it, I know it's due tomorrow for the midterm. How would you like it to be turned in? Would you rather it be all turned in one email or?
Can you do it in one email?
Or Canvas, sorry, through Canvas.
Canvas, yeah. Okay, it is going to be Canvas anyway.
Yeah, sorry, I just said email by accident.
Yeah, Canvas, yeah.
Okay, so just would it be easier just to do it all through one email through Canvas, or?
One would be fine.
Okay, all right, thank you.
All right.
Well, okay, so the one email, it's with each chapter with the key terms and exercises, right? We throw them all together.
All together,
and send it to you.
Yeah.
Okay.
Okay. All right. All right, so everybody good? I'll see you tomorrow then. So now you can go through all these chapters, save your questions, and we'll go in order. We'll start with chapter 1. We'll go 1, 2, 3, 4, just like that, okay? Okay. All right, take care.